Okay, so here we have a beam model that we used for some of the calculations. It just shows up as a line. We can see that we have a beam profile, and it's the 1.25 inches by 1.031 inches. I think it's 1/32. So thin, narrow beam, that's the stuff we did analysis with. I want to use this to do a modal analysis of that. And so I'm going to save out just the geometry file so that I can read it back in for another analysis. And okay, so notice it's coming out in a subfolder where it normally codes geometry. I'm going to put this in another folder. As you can see, it's going to save that as a space claim file. So now I'll have something that I can import into other projects. Okay, so now we're ready to start a new project, and for modal analysis I can just come and create a standalone modal analysis system, and I would create my geometry, import it, set up my model, and I can analyze that. However, if I do that, I won't be able to add any prestress and capture those effects. Alternatively, if I want to do prestress, then I need to create a static structure system. And if I just want to do that once and then be able to analyze it with or without prestress, what I can do is I can take the static structure and I can define that case, and then I will create two modal analyses. So one of them I'll drop here on the model. So you can see that that wires and connects model, geometry, and engineering data. And that will not use a prestress. And then I can do a second one, and I will drop that one on the solution. And you see that'll insert a new one, and you notice the solution also comes into the setup. So in that case, and I'll go ahead and label that one prestress. And so that we have, we'll be able to take into account the load, say of a centrifugal load that we apply to the system. As such, this modal analysis here, so let's just label modal, will do the same function as this one. So I'm not going to leave in that initial one that I created. So I'm just going to delete that. So again, this is there for convenience and be able to analyze it both directions. So let's go ahead. I'm going to import geometry. Since I saved out that file, I'll get my still beam. Okay, so it's imported the geometry into both of those analyses. Let me go into open up ANSYS Mechanical, and we can go ahead and set the boundary conditions and create a mesh in ANSYS Mechanical. Okay, so here's the ANSYS Mechanical section that we have. And you'll notice that I have three tabs in here. But let me just collapse those so you can see that. I have the static structure, which I can use for preloads, modal, and modal 2. So this one, you can see it has prestress from the static structural, whereas the other one says prestress none. So I can go ahead, and I don't have to go back and keep reopening mechanical, but I can do all of the analysis here at this time, and they'll all share the same mesh. But I can change some of the boundary conditions there if I wanted to. So let's go through and go ahead and show you how we would create that. So mesh, I can use. So let's select our line. We'll create our mesh, apply, and now we'll set a size. We'll use the default size there. Okay, now we need to set up our boundary conditions. So if we're going to simulate a cantilever load, then a cantilever beam, so let's do a fixed, I need to select my node, so I'll fix that end, apply the geometry, and now we could have lots of different kinds of loads. One that we're going to see in the analysis of the CD disk is an inertial load. So let's go ahead and create an inertial load here. And what we can use is rotational. You see acceleration, Earth's gravity. So I can set my acceleration in any direction. I can use standard Earth gravity, which is a special subset of acceleration. I can do rotational velocity, steady state centrifugal force, and then the rotational acceleration, which would add to that. So we're going to look at rotational velocity so we can see the impact. And what we're going to do is we have to define a location that it's rotating about and a direction. So let's rotate this. Let's look at our mesh. And the reason I want to look at the mesh is that helps me see the orientation of my beam in this case. So make sure I'm bending that. So I want to rotate around the z-axis. Okay, so let's come back to rotational velocity, and I'll rotate around the z component, and we'll go ahead and just put 100 radians per second in there. All right, so I have I'm stable. That's one of the requirements of modal analysis. I fixed it, so it's no rigid body rotations. I've added a stress that I can use down here in my pre-stress, and be helpful. Probably would like to know what my stresses are going to be like in the beam. So I could go ahead and create a beam tool, because that's where I needed to create stresses. You notice that the stresses don't plot here because I've got a beams, and so I can use the beam tool, which you can access here, to look up stress plots. And there's actually a number of options, so it automatically inserts a few of them. And let's also add the total deformation. Okay, so I've solved that first part, and I could just go ahead and solve the steady state. And that should go fairly quickly. And now I see I've got my green checks. So indeed I see that I have more stress at the base, less stress at the tip. And I can look at some of those magnitudes, and I can see the deformation, which is quite small since this is all linear. Okay, so we've got a basic analysis there. Now for the modal, there's no pre-stress. I have my analysis settings. Now here, something I want to look at. We have the max number of modes defined. So it's essentially, it'll calculate as many modes as you ask for. 6 is not a bad default. Okay. And then what we're interested in is the frequency of those modes and the shape of them. So I should plot some deformations. And if you notice, it's going to do this for a particular mode. So the easiest thing is going to be to copy this, duplicate these, and the nice thing is I'll go ahead and use that 1 through 6, and now I'll just change the mode for each one of those to match the number, so that it'll be easy. Save me renaming them. And go ahead and solve that. Just took a couple seconds. Let's look at these modes. This scale, it's hard to see what is happening. Okay, this is actually 0 hertz. Okay, so this is, I have to go in, and it's not, I needed to go in, it's treating this as rigid body. So this is essentially 0 hertz, and so I need to go through and add a support in there, since this is not fixed support. Since that was not, I didn't carry forward the solution into this analysis, then I needed to set a boundary condition. Okay, so let's resolve. So again, I saw that because I had virtually 0 frequencies and I wasn't really seeing a clear deformation or change of shape. So let's look at it now. That's a more realistic shape that you would expect from a beam, right? It's bending, cantilever beam. And we could see a second mode, the third mode, and they keep getting more complex. Okay, so that's a torsional one. One of the things you'll notice is that the scale of these doesn't make a lot of sense because these are essentially vectors, deformations, eigenvectors, and the frequency is an eigenvalue. Right? And they're all over the place as to the magnitudes. But you don't pay attention to that. You're interested in the shape, understand what's moving and what isn't, and then the frequency. And you notice that the first one is the lowest frequency. As we go up to the 6th mode, it's getting to a higher frequency. These are things that we would expect to see. And this data, this frequency data, would be the dominant thing you're looking for, though often you also want to compare and look at the modes to see, because some modes may be of more interest than others. Now I do notice here with these elements, I wonder if my mesh is adequately converged. So this is mode 4, it's just under 60 hertz. Let's try updating our mesh. And again, I'm going to go ahead and decrease it by a factor of 4, since this just calculates so quickly with the beam node. Usually though, you'd want to do it for at least a factor of 2 updates. Okay, so now let's come back to these modes, and it looks smoother, but you can see that the change in frequency was negligible. So I'm well converged in terms of the frequencies, even with the coarser mesh. So the graphics just didn't illustrate the curvature that was being calculated effectively. So that's the unstressed value. Now let's come down here and look at the same with the prestressed value. We'll just go ahead and create the plots. Again, we'll choose the mode that we want to look at with each one. And right click and we'll solve this case. Okay. So you can see now there's a substantial difference in the frequencies. So this one is at 16.4 hertz, whereas without the pre-stressing it was at 1.74. Let's go to mode 6. It's at 110 hertz with pre-stressing. It was at 70 hertz without it. So, and you notice it's a different shape. So the mode shapes are different in mode 6, whereas here it's going side to side without pre-stressing, and it's an axial mode here. So that's a twisting. So now the twisting mode wasn't much affected by the pre-stress. So you see that twisting mode, mode 3, is at 66 hertz. And let's see, that twisting mode here was at 64 hertz, so it didn't change much. and that's a good thing to observe, is that different modes will be affected differently by the prestress that's put on them. So there's a quick example of doing modal analysis with prestress and post-processing the data. Now, I could come in and put, for example, this, I might want to do a study, so I could come in and make my rotational velocity, make that magnitude a parameter, and now, and let's put the, let's see, define where to put the, so we can put the frequency as a parameter, and I could go through this for some of the others, and then I could run a simulation to see how those frequencies varied with the speed. Okay, so I've made my pre-stress frequencies, all the frequency down here, a parameter. No need to do that for the unprestressed, because that will not change as I change those values. So I can come back now to the to this. I can open my parameter set, and let's scan over here. You can see that my input parameter, it's white because I can change that. So let's do this. And things like this, I like to do in increments of roughly double as we scan through there, because usually the response is nonlinear. And I have here all my frequencies, so I can then just hit to, I'm going to go ahead and save my project, and then I can run. So I'll just update all design points, and we'll give that a minute to solve, and then take a look at the results. So now I've finished the solution, and I can see I varied my speed from 10 radians per second to 320, which is roughly 100 RPM to 3,200 RPM. And we can see we have deformation. So I started here, deformation 6, that's modal frequency 6. You can see that one was unchanged. Well, let's see. That's probably, I think that's from one of the, I think this solution here is from the unprestressed case. So here's the one for the prestressed case. You can see that it actually, it started out, this is the first one at low speeds, at around 70, and then increased slowly at first, and then took some big jumps up to 230. P5 changed slowly, and then some big jumps. There's probably some change in swapping of which mode is on which one, and that's why there appears to be some nonlinear jumping here. If we come all the way down to the first frequency, you can see it was around 1.7 hertz when it was unprestressed. Now we're going from 100 RPM for around 2.5 hertz, and it risen all the way to 51 RPM. So you can see the differences it gets. So you could easily extract this data and make some plots of it to see where these frequencies might be excited, where they might overlap, for example, with a spinning shaft or other thing that would that might excite those frequencies and increase the stress significantly.